Hi, everyone. Welcome back to Organic Chemistry in 5 minutes or less. Today, we'll be talking about conformational analysis, focusing specifically on angle strain. So here are the basics. Angle strain is a component of strain energy that results from the actual bond angles in a molecule deviating from ideal bond angles. First, when we think of a molecule like methane, for example, the carbon of this molecule is sp3 hybridized. This means it has a tetrahedral geometry, and its bond angles are 109.5 degrees. There are molecules, though, that have sp3 hybridization, but have angles that deviate from this 109.5 degrees. Let's go through some examples. Okay, cyclopropane is a cyclic molecule. The ane suffix is used because all of the carbons are saturated. So here, in a simple triangle, we can deduce that this angle is 60 degrees, right? And this carbon has a hybridization that is sp3, which means it should have 109.5 degrees, but instead, it's 60 degrees. And this difference in angle is what's known as angle strain. And why is this higher in energy? It's higher in energy because the angles that flank either side of that carbon, which I'm going to show here in black, are closer together to one another than they would be if they were 109.5 degrees. And remember, there are two electrons in each one of those carbon-carbon bonds, which means we're pushing those electrons, which are negatively charged, closer together, and that results in a structure that's higher in energy. Let's now compare cyclobutane. All right, so cyclobutane is effectively a square. Its real conformation is known as a butterfly conformation, but we're not going to talk about that today. That'll be in lecture. This angle, if it was a square, would be 90 degrees. And again, this carbon, right, is sp3 hybridized, which means it should be, again, 109.5 degrees, but instead, it's now 90 degrees. Okay, so it's closer now to the 109.5, but still doesn't exactly match it, which means that this structure is also going to be high in energy due to angle strain. Going to another example, cyclopentane, right? So here, this bond angle is 108 degrees. Now, this carbon, again, should be sp3 hybridized, which means its bond angle should be 109.5 degrees, but instead, it's 108 degrees. So this structure is a lot closer. So this bond angle is a lot closer to the ideal 109.5 tetrahedral. These bonds have a closer angle between them than they would in the ideal tetrahedral geometry. So this also has some strain energy. Now, if we can quantify some of this energy, cyclopropane has a strain energy of about 27 kcals per mole, which is a lot of strain energy. Cyclobutane has a strain energy of about 26 kcals per mole. And cyclopentane has a strain energy of about 5 kcals per mole. And if you find it interesting that cyclopropane and cyclobutane have nearly identical strain energies, but very different bond angles, you'll want to tune into the next episode, which will talk about the roles of torsional strain and steric strain in determining the overall strain energy of a molecule. And exceptions, well, I'll give you a little preview to the subsequent lectures. Torsional strain helps to explain the similarity between cyclopropane and cyclobutane's strain energy. And steric strain can be used to tune these different strain energies. Strain energy is also really important in organic chemistry because you can think of these molecules as being strained in the way that a spring is strained. It's going to release a lot of energy once you release the spring. And that's what happens in these molecules when they combust or they undergo reactions. There's a lot of energy that's given off starting from such a strained compound. So you can really use this to drive reactions. So tune in for the rest of the discussions on strain energies and how to understand ring strain, steric strain, and angle strain, and how they all fit together. That's been Organic Chemistry in 5 minutes or less. See you next time.